Hello everyone, I'm Weilin Zhong from University College Dublin. Today I will give a presentation about the work Voltage Stability Enhancement through Active Power Control of Converter Interface Generation. This work is finished together with Georgios and Federico. The paper investigates the ability of converter interface generators to improve the stability margin of power systems by adjusting their active power injections at their points of connection. To this end, a voltage magnitude active power control scheme is examined and its effectiveness is tested considering different topology and CIG reactive power capability scenarios. The focus is on the effect on long-term voltage instability due to the system reaching its loadability limits, as well as on small disturbance, short-term instabilities, rising in the form of half bifurcations. Simulation results are based on a continuation power flow analysis carried out considering a modified version of the IEEE 39 bus system, where a portion of synchronous machines is replaced by CIGs. Now, I will introduce the theoretical background of this paper. Considering that a CIG is directly connected to the power network, as shown in this figure, we consider two extreme cases for the feeder that connects the CIG to the network, namely purely inductive, which means the CIG is connected to at the higher voltage transmission level, and purely resistive, the CIG is connected at the low voltage network. Then we have two sets of power flow equations and we can calculate the solutions of the voltage magnitudes at the bus edge for both inductive and resistive network. These equations indicate that the higher the resistance, the more VH is affected and can be regulated by pH. This is the first property that we exploit in the remainder of this work. Here is the block diagram of the CIG controller in the paper. It consists of an inner control loop that regulates the components, ID, IQ of the current in the DQ reference frame, a voltage control loop that adjusts the bus voltage arrow through a PI and a washout filter connected in parallel. P reference and Q reference are the CIG's active and reactive power references. In conventional power systems, bus voltages are typically regulated through the variation of the available reactive power, VQ. An additional channel that regulates the voltage by modifying the active power reference, namely VP, is employed in the CIG controller. The resulting CIG control structure will be referred to as VQ plus VP control. This is the test system considered in this paper, a modified version of the IEEE 39 bus system, where the synchronous machine at buses 30, 37, and 38 have been replaced by CIGs. The voltage controller of these which are represented using the model described on the previous slide. Let's evaluate the performance of the proposed VQ-P controller by a continuation power flow analysis. The VQ-VP control is compared to the VQ control, as well as the scenario in which the CIGs do not provide voltage control. The voltage at load bus 28 and the active and reactive power output of the CIG number 3 as the loading level of the system is increased. Results show that the stability margin of the system for each of the exam scenarios is given by the respective Hopf bifurcation point. The VQ-VP control provides a significant improvement to the system stability margin. See the first figure. Moreover, this improvement is achieved without a need for large variation of the CIG's active power generation. See the second figure. The later point is very important if a VQ-VP control is to be implemented in practice, where CIGs often operate with a limited active power reserve. Finally, it is worth noting that The VQ-VP control improves the stability margin even if generator and controller dynamics were not taken into account. This is also shown in the first figure where the saddle node for the VQ-VP control is encountered for a loading level that is higher compared to the node control and VQ control scenarios. Similar conclusion can be obtained for the higher resistant inductance radial network. In a resistive network, the voltage has stronger sensitive with respect to the active power than the reactive one. So, as expected, the controller improves the voltage instability margin more significantly in a higher RX radial network. A relevant remark is that the reactive power of CIGs might be limited by the line impedance, so we further evaluate the suitability of the proposed controller under limited reactive power generation. Results show that the reactive power limits compromise the performance of the VQ-VP controller, and the maximum loading level is met at the point where the reactive power output of the CIG reaches its maximum. However, compared to the conventional VQ control mode, the limited VQ-VP control still provides a higher stability margin. In conclusion, this paper proposes an approach to improve stability of power system through active power control of CIGs. A continuation power flow analysis is carried out, considering the effect of different contingencies and network characteristics to evaluate the performance of the proposed control method. Results indicate that with the proposed control, both hop and saddle node bifurcations are encountered at higher loading levels compared to the standard voltage reactive control approach. Future work will focus on implementing a more detailed control design based on the proposed approach, as well as testing its robustness under different disturbances in transient conditions. Thank you very much for your attending.